Welcome to CS3308 Information Retrieval. This is the Unit 5 lecture part 2. And during this lecture, we're going to cover the concept of safe ranking. Now, in the previous lecture, we talked a little bit about what safe ranking is. Safe meaning that when I select the top 100 documents that match the query terms that I just specified in my information retrieval system, I am guaranteed that those in fact are the top 100 most similar documents to the query terms that I specified. Unsafe, on the other hand, says, I'm going to take some shortcuts, and I'm not so worried about it being 100% accurate. Maybe it's okay to be 90% accurate. And depending upon the kind of application, it might be perfectly fine that I don't have exactly, precisely the most 100% accurate list of documents. So safe is really about finding a way that we're going to evaluate in some fashion all of the documents to ensure that the ones that we're returning are in fact safe. Now, again, when we output the top K documents, and again, we talked a little bit about K being some number, and that number is really going to be dependent upon the kind of an application that we have, and maybe we're going to want to sit there and say that K can be equal to 10. What that means is that this whole query process is going to go out and it's going to identify 10 documents, it's going to return them to us. Maybe K is equal to 100. That means it's going to identify and return 100 documents. We talked a little bit about how when you look at Google, you'll see that it has kind of this next functionality, right? So it returns some number of documents, and then it has the next button at the bottom. And essentially what's going on there is it's saying, I'm going to return the 100. My K would be 100, or the K is 50, or however many Google is returning now on a page. But if you ask for more, I'm going to repeat the query. I'm going to eliminate the top 100, and I'm going to go for the next 100 or the next 50. So it's essentially the way that it works. So if we are going to compute all the n cosines, if we're going to be safe, or if we're going to guarantee that we have it, do we have to compute all n cosines? And essentially the idea is no, and we are going to have to look at them in some fashion. Now, first of all, the only things that we're ever going to return is we're going to return those documents that actually match the query term. So that obviously is going to narrow it down some. It can still be a large list, but that's one of the first things that we can do to narrow it down. So we're only going to return those documents that actually match the query terms. And some of the techniques that we're going to explore kind of look at how many of the terms does it have to match? Does it have to match all of them? And maybe that's the first thing we look at, is to say, hey, I only want to grab the ones that match all of the terms that have been specified. And then if I don't have enough, then I'll start taking those that maybe match fewer than all of the terms. So that's one of the things that we can do. And then the other thing that we can do is we can start looking at pruning methods. Now, we're going to get into that in just a minute. Before we do, when we start doing this, there's basically two different ways that I can retrieve the top K document from a cosine perspective. The first one is that I can take all of the terms that match, compute the cosines, and sort the results. So sorting is absolutely one thing that we can do. The only problem with sorting is that when you go to sort, it can take a long time if there's a lot of results. So depending upon the nature of the system and what the time has to be in terms of returning results, which generally is going to be short, sorting may or may not be a good solution. The alternative to this is to try to intelligently select the right ones. Can we pick off the documents that just have the highest cosine values? And this is sometimes a better strategy. Now, the question then becomes, how do I do that? And we can look at a couple of approaches to do that. One of them is this whole idea of using a heap. And so, if I have a couple of terms and I have some weights on those terms, I kind of will have a pretty good idea, based upon those weighting of the terms, where that cosine is going to fall. So one of the things I can do is that I might calculate one, and if I find that the weighting is less than one that I've calculated, I can kind of prune that one away. I mean, if it doesn't really make sense to calculate it because I already know it's going to come out less. So that's one of the things that I can do is prune that way. And then another thing I can do is every time I do, in fact, compute one of the cosines, I can build a heap structure, right? So when I'm calculating, I'm going to only calculate it once, and I'm going to put it into this kind of a structure, and then when I need to go back and take my top k of 100, right, I have a way of selecting just the top ones, and I don't then have to sort it. Now, for those of you who've had the opportunity to go through and take the analysis of algorithms course, and we went through graph theory, and we talked a little bit about divide and conquer, and branch and bound, and with pruning, and you're kind of wondering, how am I ever going to use some of these concepts? Here's a great example of how we can use some of those concepts to make our selection process in a information retrieval solution a little bit more efficient. Now, one of the things I'm going to ask you to go look at is a technique for actually scoring and sorting. It's referred to as WAND. It stands for weak and or weighted and scoring. It's all based upon DAT, or document at a time scoring. And the basic idea behind it is it's an implementation of a branch and bound algorithm. So for those of you that have had the analysis of algorithms course, you probably remember back to the whole concept of branch and bound, and the fact that we can identify branches, and we can have the concept of a bound, an upper bound or a lower bound. So I know that if it's going to be worse than something that I've already calculated, I don't even need to calculate it, right? So it's a way of eliminating some of the processing. There's an excellent paper on it. It appears over at this web link, so I would urge you to kind of jot this down, or maybe even stop the video at this point. Jot down this particular URL and go read the paper, because it provides an excellent description. It's an academic journal paper on this WAND technique. Okay, and this kind of provides us with a great example of a way that we can take a algorithmic approach, in this particular case branch and bound, and use it to make this selection more efficient. Now, keep in mind, we're not going to ever have something that is less than optimal here. Keep in mind that the whole concept behind branch and bound was that I'm establishing the bound, the upper or lower bound that I'm working from, such that I always know that I'm going to prune stuff that has no chance of being one of the better ones, right? So it's I'm gonna have a threshold. I'm gonna start pruning stuff when I get near that 100 mark, and I know, using branch and bound, I know that certain things, since they're lower in probability, or their cosine scores are going to be lower just simply because their weights are lower. I don't even need to calculate them, right? And that's one of the advantages of kind of organizing all of the weights as a tree structure. So again, please read the paper, kind of understand what we're doing in this particular methodology, and we're going to pick up this conversation in the lecture part 3, where we're going to look at the unsafe retrieval process.